স্যার এবার তাহলে শুরু করছি 10টা 3 বেজেছে।
দেখুন
হ্যাঁ ঠিক ওকে okay hello good morning everyone, welcome to the international webinar on Rendezvous with quantum physics. On behalf of the organizing committee, myself Saptaki Kaur, and assistant professor of physics from Aghorekamini Prakashchandra Mahavidyalaya. Thank you all for joining with us today. So I request all the participants to kindly keep their mics off because it's an online platform. So we'll try to avoid all these disturbances as much as we can. Now, from the title of the webinar, you can see that this is basically on quantum physics. We get to know many interesting aspects of the quantum physics, a field which we know to be one leap from old Newtonian classical physics, right? So now for today's schedule, we have 2 keynote speeches by Dr. Soham Ghosh and Dr. Orijit Shaha, followed by 2 short presentations by Mr. Anupam Shaha and Dr. Pompa Pal Goswami. I thank our honorable principal, Dr. Paramartha Ghosh, to be present with us here. Dr. Ghosh will formally start our technical sessions with his introductory note to all of us. Now, before I ask him to take over, I would like to beg your pardon to just buy a few minutes to just disclose to you that there is a sad incident that occurred to our college just 3 days back. Actually, our very dear former faculty, Professor Rajesh Karmakar, who was currently at Belur Vidya Mandir as an assistant professor, passed away due to COVID infections. So we believe this is not just a loss for his family or his colleagues like us. It's a big loss to the community as a whole, because whoever knows him knows that how nice, wonderful, friendly person he was. So our principal sir will say a few words about Rajesh da before giving the formal introduction to the webinar. So sir, I request you to now kindly take over the session and then start. Sir, we cannot hear you.
Good morning, everybody. At the beginning, let me welcome all the participants who have gathered here to take part in this first international webinar organized by the Physics Department of Aghorekamini Prakashchandra Mahavidyalaya in collaboration with Internal Quality Assurance Cell of this college, and to be held during 12th and 13th of June 2021. As you have already informed by our convener Dr. Saptaki Kaur that we had a sad incident. Actually, at the onset of this seminar, I, as a principal of this college, like to share very sad news with all of you present here. Just 3 days ago, one of our teachers of Physics Department, Dr. Rajesh Karmakar, who got transferred from our college to Belur Vidya Mandir a few years back, has died untimely due to the deadly virus COVID-19. Dr. Karmakar was a brilliant student and researcher, and also was very successful and student-friendly teacher with charming personality. He was not just a good academician, but was a nice human being with very honest and positive approach in all respect. We, his colleagues in this college, lost a very good friend like him and are very much shocked, deeply shocked due to his sudden death. As a mark of respect and love to the departed soul, we shall request all the participants here to remain silent for 1 minute, and after that I shall continue my brief presentation. Yes, the time starts now. Yes, it is over. Thank you all. Now, I would like to thank our faculties from the Department of Physics, particularly Dr. Saptoki Kaur, convener of this international webinar, for organizing this mega event. In this regard, my thanks also goes to the IQSC coordinator of our college, Dr. Ashish Kaur, Associate Professor in Mathematics. I like to offer my heartfelt gratitude and thanks to our speakers of today's seminar for being agreed to deliver speeches before the participants, and I cordially welcome them. I also welcome all the participants of this webinar along with all my colleagues and students attending this event of academic exercise on virtual mode. Friends, you all are aware of the serious pandemic situation. Educational institutions are trying to maintain their connect via this type of online platforms instead of the conventional classroom teaching, seminars, etc. The same is true for our college as well. But apart from providing regular online teaching sessions, here is an endeavor from the physics department of our college to try something bigger with an aim to engage students, teachers, and researchers in fruitful and illuminating science discussions for a while. In doing so, we hope to rekindle the inner urge of the participants for further exploration, further exercise or study, whatever appropriate. That is something somehow getting subdued these days due to prolonged homestay. I shall take the opportunity to talk a bit about our own college Aghorekamini Prakashchandra Mahavidyalaya. Aghorekamini and Prakashchandra were the parents of our great leader and ex-Chief Minister, late Dr. Bidhan Chandra Roy. Situated at Bengai, Hubli, our college is very close to Kamarpukur. All of you uh, possibly you know Kamarpukur, the birthplace of great Sri Ramakrishna Paramahansa. We have a beautiful and large college campus that hosts large playgrounds, ponds, and a huge indoor sports complex with gymnasium. I cordially welcome you all in our college campus, either for academic or for non-academic visit. Now, I must talk about the wonderful speakers who agreed to be a part of this webinar and illuminate us with their lectures. As I see the list, I find that even one eminent researcher from the opposite end of the world is gracious enough to take part in this event. I welcome Dr. Soham Ghosh, a postdoctoral researcher from Lawrence Berkeley National Laboratory, California, USA, for joining us and being a keynote speaker for today's session. I am honored to welcome Professor Arijit Saha of Institute of Physics, Bhubaneswar, Odisha, and Professor Ananda Dasgupta of Indian Institute of Science Education and Research at Kolkata. The other two keynote speakers in this webinar who managed to find time for us and enlighten us by the lectures. There are also young college professors Dr. Somnath Jalal and Dr. Amit De who agreed to give two contributory talks, and I welcome them as well. I am very happy that not only faculties, even the students also came forward to give short presentations in our webinar. I am eager to listen to student participants, Mr. Anupam Saha, Dr. Pampa Pal Goswami, and Mr. Rajdeep Banerjee. Lastly, thanks to Dr. Sampa Mondol, a physics faculty of our college, to find her time to end the webinar with her talk. Though it sounds more like a vote of thanks, I preferred not to miss the opportunity to express my sense of gratitude and thanks them all in the beginning of the webinar. I again welcome you all the speakers as well as enthusiastic participants, and I hope this webinar becomes a grand success. As I am a teacher of geography and do not have much knowledge on physics or quantum physics in particular, I henceforth would like to take the position of a learner alone and eagerly wait to see how the whole event unfolds. So, thank you all very much. Namaskar.
Thank you, Principal Sir. That was a very nice introduction. and also it was very inclusive. You actually mentioned all of them, and then also said all the relevant things. So thank you so much. We'll now move on to our technical session. Just 1 second. Okay, so now we have lined up now the keynote speech by Dr. Soham Ghosh. Hopefully, Dr. Ghosh is with us. Soham?
Yes, I'm here.
Okay, thank you so much. Okay, so Dr. Soham did his BSc from Presidency College, Kolkata, and then his MSc from IIT Kanpur. And after that, he went to Florida State University and got his PhD in theoretical condensed matter physics from there in 2017. Thereafter, he was a postdoc for 2 years at University of California, Davis. And since last year, he is working as a postdoctoral fellow at Lawrence Berkeley National Laboratory, USA. I should mention here that I have a special connection with Soham, as both of us did PhD from the same place under the same guide. So I am actually very much delighted that Soham agreed to give a talk in this webinar, and we all will be very eager to listen to Dr. Soham's talk. Thank you so much, Soham. The title of the talk is Stability and Electronic Structure of Oxide Surfaces and Interfaces. So I would now like to request Dr. Soham to please take over the session and deliver his speech. Dr. Soham,
thank you. It might take me a few seconds to figure out how to present on Google Meet because I've never done this before.
Okay, so you can see on the bottom there is a something called present now. Maybe it's not written, but there's some icon. If you just put your
I can see I can present my entire screen.
Yeah, and then on the entire screen you can just put you can then minimize it, and then go to your basically open your slides. So because you are now that way you can do, or
Wait.
Yes, and then just minimize this screen and then open your presentation.
Okay, a better way is to be able to present only a specific
that
tab.
Also you can do. That also you can try. See, then not doing the whole screen, if you can only choose the slides.
Hold on. Let me see. Give me 1 minute.
Okay.
I don't see the option, but that's okay. I can share my entire screen. That would work.
Okay.
So can you see it now?
Yes, we can see it.
Okay. I think the only downside of this is, actually there is no downside of this, is that like if I have to find something later on as we talk, then you will be tagged along with the ride. So
it's visible quite. It's quite
okay.
Visible.
So everything looks good on your end?
Yes.
Okay. So one thing that Shataki didn't mention about me is that I was born very close to Bengai College. আমার বাড়ি বদনগঞ্জের পাশে শান্তিপুর বলে একটা গ্রাম আছে ওখানে।
I forgot to mention that.
তো আমি কামারপুকুর বহুবার গেছি কিন্তু বেঙ্গাই আমি কোনোবার যাইনি। Okay, back to technical topics. So my talk, I decided to title Oxide Surfaces and Interfaces, which is what my PhD was on. And I mostly studied electronic structure and stability and ferromagnetism as well. And I used a tool called density functional theory. Now, because Shattagida told me that this
Yeah, we can hear you.
Okay.
No problem.
So I was told that this is a talk where college students, physics undergraduate students would be presented. So my talk has 0 equations. I hope that is okay. So if I may go over the outline of the talk, what I thought I would do is start with a primer to condensed matter. A very short introduction to what condensed matter or solid state physics is, and using that as the foundation, I will go over two different but related topics. One is the interface between something called strontium-2 ruthenium-O4. In short, it's called SRO, and a ruthenium metal inclusion. This is a hybrid material of both metal and metal oxide. It's grown in situ, and I have an electron microscope picture that will make it clear later on. And the second topic is a story of a 2-dimensional electron gas in an oxide called strontium titanate. Between these two, the basic discussion will be on vacancy structure and ferromagnetic instability, and then I'll conclude. So I think I'm going to start with the primer to condensed matter. Actually all of this will be known to many of you, and some of this will be probably known to all of you, but probably it's better to do a quick recap. So the major goal of solid state physics is to find good quantum numbers. What are good quantum numbers? Good quantum numbers are eigenvalues and observables, in the sense that if you have a device to measure anything in a material, the device measures an observable, and that observable is the steady state eigenvalue of a certain thing. So that eigenvalue can be anything. It can be energy, it can be magnetic moments, it can be spin. So what good quantum numbers are eigenvalues, and eigenvalues are what you essentially hope to find when you do condensed matter theory. Now, quick note about electrons in solid state is that electrons are fermions. So why does that matter? It matters because unlike bosons, fermions, if you look at the image on the right, the middle one, fermions occupy distinct states. You won't find fermions all collected in one energy state. So the middle picture on the left is bosons, where they all go together in a single state, and fermions like to stay in separate energy levels. Now, without any potential, the electron is called a free electron, and it has a certain dispersion relation. Dispersion relations are basically energy momentum relations. So dispersion relation will tell you how much energy an electron has if you know its momentum. Now, in a free state, that looks like a parabola. But if you impose any potential on it, then you get what are called quantized states. So then you no longer have the momentum as a good quantum number. Then you'll get different types of good quantum numbers which will look like momenta, but they are not exactly momenta. You can call them crystal momenta, and people do call them crystal momentum. So these are the Ks in the top left picture. So instead of having a free parabola, what you get are distinct quantized states, and you get wave functions which look like the pretty picture on the top right. So the point of this is that pretty much all of condensed matter is to impose restrictions on the free electron, and as you continue to impose restrictions, you will continue to see energy levels change, and you will continue to find different good quantum numbers. So what is a good quantum number for a free electron is not a good quantum number for a metal, which is not a good quantum number for a for a solid which is highly magnetic, for example. So now all solids have a basic criterion, which is that you can pretty much start the physics from a particle in a box, which is one of the introductory quantum mechanical systems that people learn, and then impose, instead of just one box, you impose a periodic potential, which is this picture on the bottom right. So you have ions in repeated periodic intervals, and the ions have very negative potentials, so you can call them potential wells. And in those potential wells, electrons stay trapped. And because electrons are fermions, they don't stay trapped in the lowest level. They form distinct energy levels, which are drawn in these lines. And then when you bring all these ions together and form a solid, then there is interaction between these levels. And these interactions give rise to energy levels and what are called band structure, which is one of the fundamental things that condensed matter theorists look at. Okay, so what happens, what I just said in pictorial form looks like the image on the top. So you have free electron-like wells, you bring them together, and when those wells touch each other, you create what are called gaps, because electrons don't like to cross the levels. One of the things you realize when you do quantum mechanics is that electrons do not like their energy states crossed, and they find ways to create gaps between their bands. So the gaps here are denoted in red color. So if you put a bunch of ions together, the electrons will find ways to avoid each other's energy levels and form electron bands. Now people usually look at it from two different angles. One is called weak binding or nearly free electron, where you say that the electron is almost the same as a free electron, but then you have a very tiny periodic potential. And the other way to do it is to start from what is called tight binding. In tight binding, your electron levels are very distinct, and whatever happens afterwards is treated as a perturbation. But the important thing is that these two pictures lead you to the same conclusions. You can start from either a weak binding picture or a tight binding picture, and you should get the same answer at the end. People use one or the other depending on what they're looking at. For example, weak binding is great for an overall description of solids, especially metals. And in those metals, what you have because of periodic potentials is called block states. And from block states, you can calculate bands. And that's the general way people attack this problem. But tight binding, on the other hand, is great for solving additional interactions. For example, Satyaki Kaur has done a lot of work where he starts with a tight binding model and in which one of the part of the Hamiltonian is perturbative. And then usually what happens is that you open up gaps. So these are two different styles of attacking similar problems. It just depends on which one is more convenient for you. Okay, so that is the overall picture of how condensed matter is studied. The specific technique I use is density functional theory, which I'm not going through here, but if somebody wants to talk to me about it or ask questions about it after I'm done, I'd be very happy to talk about it. So the first topic that I studied was the interface between strontium ruthenate and ruthenium metal inclusion. And that has implications for its superconductivity, which I will talk as I go through it. This was done at Florida State University, and my co-workers are mentioned. So this is an STEM image. So it's a scanning tunneling microscopy image. It's an electron microscope image. You can see that it's a very, very fine image. So the scale on the right, so the top picture is actually not that fine, because it's the scale is 15 micrometer. But the bottom picture is extremely detailed. So that scale goes all the way down to 1 nanometer. So the white dots you see are actual images of real atoms. What you are looking at is the electron shining out of the electron cloud of the solid atoms themselves. So in this picture, the shiny dots are ruthenium metal, and the gray or black part is strontium ruthenate, the oxide. Now, if you zoom into it, which is in image B, the inset, you will see that you have a periodic structure of some kind. So you have one layer of strontium ruthenate, and then 2 oxygens at the boundary, and then another layer of strontium ruthenate. Now, what are the implications of it? The implications is that strontium ruthenate is a superconductor. It's actually an unconventional superconductor, but you don't have to worry about what unconventional superconductivity is. Just know that it is a superconductor. But if you have these metals inside this oxide, then you have a superconductivity which is, instead of 1.5 Kelvin, it becomes 3 Kelvin. So it's a doubling of superconducting critical temperature, which is somewhat strange and somewhat not common. And it also has a hysteresis loop, which is also not common for superconductivity. Now, what you can do with DFT is to find out what the structure is. And that's what I have done. So this is a representation of what the same structure looks like when you do a DFT simulation. It's the exact same structure that you saw in the STM, except now it's in a simulated environment, in a computer. So what you do is look at the bottom 2 pictures. You take part A and you take part B and bring them together, and then you add the 4 oxygens that sit in middle. And then you try to do a stability analysis and see if the electron is stable. So essentially you calculate the enthalpy, and if the enthalpy is negative, then the system is stable, and if the enthalpy is positive, then the system is not stable. This is nothing more than simple thermodynamics. It turns out that the system is not just stable, the system is far more stable than any other type of interface you can create. And what's more, what you can do with simulations is look at things that you cannot see with electron microscope. For example, this is the BC plane, which you cannot see with electron microscope, because the electron microscope is a 2-dimensional picture. So this is the dimension that's hidden. But through simulations, you can see that you can find out what the oxygens are. For example, here you'll see that there are the oxygens sit immediately in the groove. What's more, you can calculate the coordination numbers. Coordination numbers are basically almost similar to oxidation numbers in solids. And when you calculate coordination numbers, you will see that oxygens have mixed coordination numbers, which is slightly weird, because usually oxygens like to be in a state of -2. So there are 3 different types of oxygens. One is in strontium ruthenate, one is in the groove, and one is inside. One is very close to the metal, and each of them have a different coordination number. Now, what you can also do is compare it with other possible configurations. So, for example, on the left is another possible configuration. It looks almost identical to the one that's seen in experiments, except it doesn't have these 2 oxygens at the interface. Or you can do what's shown on the right, where you can create a much bigger supercell. So this is 8 across and on the A side, on the A direction, and 9 across on the B direction. And you can keep doing this till you find that the structure that you see in the electron microscope is the stable structure. By finding out the enthalpy of formation of every other possible configuration and see that it's not as stable. That pretty much conclusively proves that what you see in your simulations is what you see in your experiment. But there's more. What you can also see is ferromagnetism. For example, usually strontium ruthenate is not ferromagnetic, and ruthenium metal is absolutely not ferromagnetic. One of the standard things in condensed matter theory is that if something is a metal, then it's not. Then when it becomes metallicized, then it tries to repel ferromagnetism. Although on the other hand, some of the good ferromagnets are all metals. For iron is a good metal, and it's also a ferromagnet. So what you can show here is that oxygens which didn't have any magnetic moments. So this is a density of states. A density of states is the number of states per energy level, and then when you project it onto a specific atom, then it becomes the orbital projected density of states. For example, this is the on the left is the density of states of one of the oxygens at the interface, and it's projected onto its 5 constituent orbits, and every single projection shows that there is ferromagnetism, and so does the density of states of strontium, which is on the right. And this is found only on this interface. You won't find it in either the oxide or the metal. So, but the purpose of our project when we did it was to answer the superconductivity. Ferromagnetism is good, but superconductivity is better. So, what the conventional wisdom in these materials is that the superconductivity arises from pairing within ruthenium layers, ruthenium oxide layers. Now, there is something. So what the interface ruthenium oxide layers does is it acts as an interlayer Josephson junction. Now, Josephson junctions are a device where you have 2 superconductors and you have a metal in between. And what it creates is a current that perpetually continues without any external input. But you can have an effective Josephson junctions in oxides where the layers inside the oxide act as 2 Josephson junctions, but they have to be mediated. And in this case, the mediation is done through the oxygens at the interface. And that's what gives rise to a doubling of the TC that we saw in the beginning. Now, one of the signs that we did things correctly is that you can do an experiment on the interlayer coherence length, which is the coherence length of the superconducting pairs, and you see that the coherence length increases and the anisotropy of superconductivity decreases. These two are good indicators that you have mediated superconductivity by coupling 2 Josephson junctions. So this is an example of structural relaxations and thereby investigation of different properties of a solid using density functional theorem. Next, I would like to show another example of the same technique, also in an oxide, but this time in a slightly simpler oxide. But the advantage of using a simpler oxide is that you can probe it further and you can ask more questions. So the oxide is strontium titanate. It's called a perovskite because the guy who discovered this class of material was an 18th century Russian mineralogist whose name was Perovskova. I don't remember exactly. But this class of material is named in his honor. So the 2 things I will talk about are vacancy stripes, oxygen vacancy stripes, and related local magnetization. Now, what do I mean by 2-dimensional electron gas? Now, usually electron gas is 3-dimensional. If you have electric current, if you have metals, the electrons are 3-dimensional. The reason for calling them electron gas is that the electrons are nearly free, just like particles in a gas, the electrons in a metal are almost free. There's very strong similarity between dynamics of gas particles and dynamics of electrons in a good metal. But instead of being a three-dimensional gas, this is a two-dimensional gas. So on the left is an experimental result. And on the right, on top, is an example of perovskite in a picture. And the crystal structure of the thing that we're studying is on the right below. So if you look at the image on the left, what it shows is something quite significant. So what the researchers did in 2005 was take one oxide, strontium titanate, and another oxide, lanthanum aluminate. They are both insulators. None of them are metals. But if you build layers of lanthanum aluminate on top of strontium titanate, and if you keep building them, which you can do with a very expensive synthesis, so if you add one layer of lanthanum aluminate, you will get no conductivity. If you add two layers, you will get no conductivity. If you add three, you will get no conductivity. But if you add four layers, your conductivity jumps by a factor of 14. So what you get is you add two insulators together and you get a metal. Now, this is something that is extremely rare, which is why a lot of people started studying this thing right around 2005, 2006. And I did it too when I was in my PhD. So one thing you can find when you do DFT on this material is that instead of one single band for one state throughout the solid, what do you get are sub-bands, which means that every single layer inside the material has its own energy level. And the reason for is that the field inside the HTO layers create a quantum well, and thereby it leads to quantization and non-degeneracy. And this increases as you go towards the surface. And it also depends on whether your surface is made of strontium oxide or whether it's made of titanium dioxide. So if you have this material, you can either stop the surface at strontium oxide, or you can stop the surface as titanium dioxide. Now, if you stop the surface at strontium oxide, your energy levels would look, or your bands would look like the picture on the top, where it's quite non-degenerate. But if you stop the surface at titanium dioxide, the energy levels would become a lot more bulk-like, which is one hint why you have to stop at strontium oxide in order to get a metal. Now, one of the ways you can get to these subbands is to relax the system. When you put strontium oxide and lanthanum aluminate together, or if you only have strontium oxide, the moment you create a surface, the atoms on the surface relax, and the electrons change their states due to the relaxation. So on the left are the bands for the electrons on a non-relaxed system, and on the right is the same system, but I have allowed the simulation to relax the atoms. And you see the effect of relaxation is that the bands become much more non-degenerate. The electron wells become much more defined. And so what you see in these boxes, what I call band 1, band 2, band 3, band 4, and band 5, are corresponding to these points that go from these red ones. So you can see that the lowest band, the bands that you see experimentally, sit on the surface. And that's exactly what you see with experiments. If you're certain of this, what you can do to test this is to dope this, to modify the well. So for example, I doped the titanium oxide surface with fluorine. So this fluorine sits on the surface, but the good thing about, so why did I choose fluorine? The reason for choosing fluorine is that fluorine is extremely electronegative. And if it finds any electrons around, it attracts it towards itself. And the effect you can see on the electron levels, it becomes much lower, and it draws all the excess electron bands towards itself. The field, you can increase the field strength with this, and you can occupy more conduction bands with it. And you can bring the electron gas more towards the surface. And this is not just with fluorine. You can do it with anything. For example, you can alternately replace strontium by lanthanum, and you'll see that the electrons start coming towards the lanthanum. So you'll shift the electron gas into two components. So in a way, you could call this interface and surface electron engineering. So you choose what you want to dope with, and the electron reacts accordingly. What you can also do is look at whether there is any vacancy when you do this interface engineering. And it turns out that there is not just a vacancy, there is a very specific type of vacancy. What the vacancy looks like is a stripe. So you have a layer, you have a line of oxygens missing on the surface, which is given in these red circles on top. And the result of that is that the electron gas, which leads to it being a metal, is delocalized. Those electrons can move around. But now you also create electrons which are localized and which gives rise to magnetism. So essentially what you have are these stripes where one part of the electron states become metal and move around, and the other part of the electron states become localized and create magnetic moments. So this is an example of how experiments and theory come together. For example, this is a very well-cited experiment from 2014 where they show these same bands using a method called RPES. So this shows the same bands that we can generate using density functional theory simulations. This also shows that there is spin splitting. And we can also show that. For example, on the left is a picture of the stability of the vacancy oxygens, and on the right is a picture of the bands, this time split in spin. And if you compare this levels with the experiment, you will see that they fall right on top of each other. And not just that, what you also see is that the dimensionality is correct and the location is correct. And furthermore, what you can find out is the nature of surface conductivity. What you will have, so this image is the orbital projected density of states. You can calculate the magnetic moments from this, and you can see that the most of the magnetic moments will be concentrated in the dxy states, and the dxz and the dyz will be further up. So part of the magnetism is located in dxy, and the rest of the electron states are more delocalized in other states. So this is a picture of the magnetization. So it is quite localized. It's only on the surface, and it only one part of the electron states available contribute to it. So we can also so there are some additional complications, but we showed that this is the main picture. Now, one final thing that you can do is put whatever energy levels you have and the spin splitting results on top of experiments, and you will see that there is a very good correlation. So in short, what this picture shows is that you have a metal on top of which you have localized magnetic states, and they're split because of something called a Rashba effect, which I'm pretty sure the speaker after me knows more about than me. So essentially what the Rashba effect does, it locks spin and momentum together. And this picture shows on the right that spin and momentum are indeed locked together. So in conclusion, what you can do is with DFT and in general condensed matter simulations is you can predict stable structure based on experimental studies. You can make intelligent guesses about the nature of solid states, including superconductivity. You can look at vacancies, you can look at their ordering, you can look at their stability. You can look at ferromagnetic stability and ferromagnetic instability. You can look at mixing of surface states with bulk states. You can look at splitting, and you can look at magnetic moments. And you can look at spin momentum correlations. So this, in general, is basically the beginning of density functional theory based condensed matter theory. On top of this, you can do more interesting, more subtle things. For example, what the next speaker is going to talk about. But in a sense, this is where you start from. Oh, so this is where I conclude. I don't know. Do I have some time to take questions?
Yeah, sure.
Okay.
That was a very nice talk, Shoham.
All right. Let me stop my presentations and go back to the camera.
Okay.
So how long do I have for questions and answers?
You have 10 minutes.
Okay, that's good.
Fairly, you have 10 minutes. Okay.
Thank you.
Yeah. So whatever I collected, I can say that was a very nice talk from the starting. You just took care of the very basic BSc students so that they can understand the subject matter what you are trying to say, and then rest of the talk. I would say just more glory to DFT. That's such a nice technique. So, which kind of package did you use for your getting this data? Like you
so this was done in VASP.
All of them are in the VASP. Okay.
This was done in VASP. So in my postdoctorate, I moved to doing different things. So in my postdoctorate, I started looking at superconductivity, and then I used something called quantum espresso. Okay. But in my PhD, everything was done using VASP. So VASP stands for Vienna Ab Initio Simulation Package. This is, for some reason, Vienna has a lot of people who do this kind of simulations software. You will find many DFT simulation packages coming out of that one place.
Yeah, I know that people generally start.
There are a few questions in the chat. Do you want me to address?
Yes. Yeah, means actually we have Dr. Saurabh Haldar from Mathematics Department. He's the assistant professor from Mathematics Department. Saurabh, are you here? Saurabh? Maybe he's yeah. So these are the questions. Means actually these are for you.
Okay. So do you want to read them to?
Yeah. I'll just read them for you. So the first question was from Anupam Banerjee. He said, "What is Josephson's junction?"
Oh, so Josephson junction is a device. It's an electronic device. Incidentally, this electronic device is used now by National Institute of Standards in the United States to create as a standard. So what it essentially is this: you take one superconductor, you take a second superconductor, and you put a metal in between it, and then you connect two wires. So and what happens is that electrons inside superconductors form something called a Cooper pair. So a Cooper pair is two electrons tied together. So their momentum connected together, and Cooper pairs are the basic building blocks of conventional superconductivity. They're phase locked, and so these Cooper pairs exist inside superconductors, and in a Josephson junction, these things tunnel from one superconductor to the next through the metal. So of course your metal at the junction has to be thin. If you make it too thick, then you'll kill the tunneling effect. But if you make the metal thin enough, then these Cooper pairs will tunnel from one superconductor through the metal to the next, and then come back around the wire. So what it will create is perpetual conductivity without any voltage across the junction. Okay, did I answer that?
Okay, yeah.
Anupam?
Anupam, are you happy? Anupam?
Yes, sir. Yes, it's fine. It's fine.
Okay, thank you. So we'll just go to the next question. That is
Okay.
from Mritika Ghosh. The question is, you were mentioning in the RU metal inclusion in SRO about unconventional superconductivity. So does it follow the Meissner effect? What is the unconventional superconductivity? So two questions are there.
Okay, so I think this question and the next question, what is unconventional superconductivity, are related. So I just realized that when I was speaking, I made an incredibly incorrect statement. I said that metallicity and ferromagnetism don't go together, which is a completely incorrect statement. I forget that I said that. What usually happens is that magnetism and superconductivity don't go together. You can find metals which are magnets and magnets which are metal. They happen all the time. That was a completely incorrect statement. The correct statement is that magnets and superconductors don't happen at the same time. And the reason for that is what Mritika asked. The reason, so you can see this with Meissner effect. So essentially, Meissner effect, for those who do not know, is when you take a superconductor and bring it inside a magnetic field, and the superconductor repels the magnetic fields. So in a perfect superconductor, magnetic fields cannot penetrate. Now, there is a small, detail to it. Like, there is something called a skin effect. So it can penetrate a little bit, but as it goes deeper, it can't. Now, both conventional superconductivity and unconventional superconductivity follow Meissner effect. They will both repel fields. Now, what is unconventional about unconventional superconductivity is the fact that we don't know how to theoretically represent it. So essentially, conventional superconductors, for example, mercury is a conventional superconductor. These are superconductors which can be explained using BCS theory, the Bordin-Cooper-Schrieffer theory. Incidentally, one of these, all of them got a Nobel Prize, and one of them was at FSU, the place where I did my PhD.
Is he still there now?
No, I think he died.
Oh, I didn't know that. Oh, I see.
He was in a car accident, but then he lived. But
I know he was in a car accident and he was in jail for that, right?
Right. I'm not sure. Yeah. He was in prison. Yes.
But now he died. Okay.
So so BCS is a theory of superconductivity from the 60s, from 1950, 1960. It's the only theory of superconductivity we have, and it explains the formation of Cooper pairs. So essentially, the class of superconductors that can be explained with BCS theory and are conventional superconductors. These are also called phonon-mediated superconductors because the Cooper pairs, the mediation between Cooper pairs are done with phonons. Unconventional superconductivity, for example, strontium ruthenate, are superconductors where we don't know the theory. Essentially, we do not know why they are superconductors. There are theories. I am actually not an expert on unconventional superconductivity. I don't know those theories very well. But essentially, there is no good theory for unconventional superconductivity that I know of. This is the only difference. Conventional superconductivity has a theory, the BCS theory, and unconventional superconductors are all superconductors who cannot be explained with BCS theory.
Okay, sir. Thank you.
Okay, so...
Okay, the next question was from Dr. Somnath Jalal. And that was, are you getting topological insulator where surface is metallic and bulk is insulator in this materials?
No. There is no topology in it. So topological insulators are completely different things. I think Chattoki Kaur can explain topological insulators, and the next speaker would be the person to ask about topological insulators. But there is essentially no quantized topology in my case. It's just a separation of you can call it division of labor. So so some of the electrons take part in metallicity and some of the electrons take part in ferromagnetism.
Okay. So let me go to the next. Okay, next question is a general question. I'll come back to that later, Anupam. I'll just go to the next one. So Tuhin Devnath is asking, can we achieve superconductivity property nearly at room temperature? And which material is useful for a superconductor, like metal or insulator?
So this is a question that I looked into in my postdoctorate. So in the last 10 years, there is a field of study which is called room temperature superconductivity. And the goal of those researchers is to find superconductors that can superconduct at room temperatures. And we have actually come very close. I think the record superconductivity now is 300 Kelvin, which is almost room temperature. I mean, not June Bangai room temperature, but room temperature somewhere, Alaska, Siberia, somewhere. Actually, 300 Kelvin is proper room temperature. It's not even freezing. So one of the superconductors that I studied was H3S, and that is superconducting at 260. So you can go to places where in winter you get 260 Kelvin. But the problem is that it requires a lot of pressure. So if you want to read about it, Tuhin, there is a theory by Ashcroft where he says that if you take hydrogen, just pure hydrogen, and put enough pressure on top of it so that it becomes very dense, eventually it will become superconducting. So there is a general consensus that that's what happens at the core of Jupiter, the planet. So at the Jupiter is essentially has a lot of oxygen. Has a lot of hydrogen. The core of Jupiter is essentially hydrogen, and because it's a big planet, there is extremely high pressure at the center. And so the theory is that at the center of Jupiter you have a ball of metallic hydrogen, which is superconductivity. And yes, you need a metal to be a superconductor, because to have a good superconductor, especially close to room temperature, you need a high density of state at the Fermi level. So the Fermi level being the highest occupied level of a metal. So you need a high density of states, a high concentration of electrons at the Fermi level, and you also need very strong phonons. Because you have to mediate between the electrons using phonons so that you can create stable Cooper pairs. And hydrogen or hydrogen-like materials has both of them. Because hydrogen is light, it has very high phonon frequency. The lighter a material is, the higher its phonon frequency. And you can, in certain circumstances, you also get very high density of states at the Fermi level. But I mean, when I say high, it's not as high as, say, for example, copper. High is relative, right? For example, like copper is an extremely good metal, but it's not a very good superconductor. Whereas, say, hydrogen-3 sulfide or is also a metal. It's also a but it's not as good as a metal, but it's a much better superconductor. So you need some electrons at the Fermi level to create superconductivity. A good insulator will not do it. But unconventional superconductivity, on the other hand, for example, strontium ruthenate is an insulator.
Okay, thank you, Sean.
What I just said is valid for conventional superconductivity.
Okay, so just go to the next question. That's from Rajesh Mukherjee. The question is, how many atoms did you take to make the supercell?
Also depends on which exact system you are talking about. There are several ones, but usually, so the largest ones were about 190 or so.
Okay. So then the next question is from Surojit Queen, who is also faculty here. So he's asking, Cooper pairs are most probably bosonic particles because they are two electrons are coupled with each other. Is Bose-Einstein statistics applicable here?
Yes. Yes, Cooper pairs are bosons, and they do form and they satisfy Bose-Einstein statistics.
Okay, thank you. Okay, so now then the one last question that remained, that was a very general question. So Anupam Banerjee asked, can you briefly say about density functional theory?
Oh, okay. So density functional theory is a clever way of solving quantum mechanics in solids. So now, okay, so let's go back to let's say the basics. Now, what we studied when we first started quantum mechanics is quantum mechanics of one single particle. So so it follows the Schrodinger equation, and you can calculate its eigenvalues, and then you can put it in. You can enforce different potentials on it. You can put it in a potential well. You can put it in a W. You can put magnetic moment. You can put it in a magnetic field. You can put it in electric field, but it's still a single particle, single state. So it's still a single particle. Now, in solids, you have many particles, 10 to the power 23 of that order. The problem with that is that it is impossible to solve the Schrodinger equation of 10 to the power 23 connected particles. There is no way. It doesn't matter how strong, how powerful your computer is. This is an intractable problem. This problem cannot be solved exactly. So then you have to come up with approximations. For example, nearly free electrons, where the electrons are almost free, like a gas, and then there is some small perturbations on it, is one way. Tight binding is another way. Now, density functional theory is a whole different way of attacking the same problem. What can be shown is that the density of electrons at ground state is exact. If you can calculate the density of states, that exactly corresponds to the right ground state. So instead of starting from the Schrodinger equation of 10 to the power 23 electrons, what you do is start with an approximation of the density of electrons. So you start with a guess, then you take that density of states and you form pseudo states out of it. So instead of actual electron states, you can say, here are my fictitious states. These are completely made up in your simulations, in your computer, but they look like the energy states of the atoms in your system. So you put electrons in those levels till you hit the Fermi level if you have a metal, or till you hit the topmost level if you are a semiconductor or an insulator. And then you calculate the energy out of this and see whether, and then you calculate the new electron density and you plug it back into the same equation. So this is an iterative process. So you start with one electron density, you plug it into those states, and then you enforce the potential on top of it, and you get a new density. And then you go back and doing the same thing, and you keep doing this till you end up with a density that doesn't change. The thing that made it so famous and gave the people who discovered it a Nobel Prize is the fact that there is an exact electron density correspond to the exact ground state. That is not very easy to recognize, but once you point it out, it's very easy to see that if you have one ground state, you have one exact and unique electron density. So there is so if you look at papers that come out of condensed matter, density functional theory is by far the most popular tool that people use to study condensed matter physics. It's the only tool that you have to study realistic materials. Oh, well, Hartree-Fock theory is, I mean, So the Hartree-Fock theory is essentially a perturbative theory. I mean, DFT is a technique in general. So it's the technique uses electron states as the electron density as the starting point, which is why it's called density functional theory. And Hartree-Fock theory uses one. So Hartree-Fock theory is essentially a first order Green's function theory. So you start with your first order Green's function propagator, and then you add your interaction, and then you cut it up after the first order, and you get the Hartree-Fock theory, which is great. I mean, there are a lot of chemistry computations, for example, that are done with Hartree-Fock theory. But for extended systems, for example, metals, any crystal, density functional theory is far more popular and is far more useful in understanding the properties.
Sir, does DFT theory has something correspondence with time-dependent perturbation theory? Because
Yeah.
they are also we can see the Fermi golden rule and the virtual band concepts.
Yes. So almost all time-dependent perturbation theory uses density functional theory as a platform. So almost all the time-dependent perturbation theory programs, codes, whatever you can use for simulation, has density functional theorem inside it. So if you take a system, you first do DFT on top of it, you get the ground state, and then you do TD-DFT on top of it.
Okay. Thank you, sir.
Does that answer your question?
Okay, thank you, sir.
Okay, thank you so much, Shoham, for such a nice interacting question and answer session. And in general, thanks a lot for coming and
You're welcome. Thank you for hosting me.
Yeah, giving a talk late at night. So
unfortunately, I'll not be here for the entire day because it's already pretty late.
Yes,
I'll try
of course,
to
we
stay
know that.
for some time, and then I'll have to sleep.
Yeah, I know, we know that. So I was just going to say that we'll let you go, but then you can stay if you want.
I'm quite interested in the next talk.
Okay, yeah. That was a very he was a very nice speaker, and it's a very nice talk. So okay, let me then start the second talk. Thanks, Shoham, again, and hopefully Dr.
Thanks
Shah is
the
with us.
organizer and the principal. Thank you so much for hosting, and thank you for organizing this.
Thank you, Shah. Okay, so now we will move on to our second talk. We have our second keynote speech by Dr. Arijit Shah from Institute of Physics at Bhubaneswar. Dr. Arijit Shah, are you here?
Yeah, hi Satyaki.
Okay, hi Arijit.
Good morning. Yeah.
Good morning. So let me just give some brief introduction for you. So Dr. Arijit Shah did both his BSc and MSc in physics from Vishwabharati University. Then he went to Prakashchandra Research Institute, Allahabad, to get his PhD, and he obtained his PhD degree in theoretical condensed matter physics in 2009. Thereafter, he worked as a postdoctoral fellow first in Weizmann Institute, Israel, and then in Basel, Switzerland. And after that, in 2015, he joined Institute of Physics as a reader, F, and then he's still there at that place. So Professor Shah is working on quantum transport, Dirac systems, and topological robustness in the field of condensed matter for quite some time now. And it's a pleasure to have him with us today. And his today's topic of the lecture is topological insulators and topological superconductors, a new paradigm of modern condensed matter physics. So I'd request Dr. Shah to kindly take over the session now and deliver his speech. Thank you so much, Dr. Arijit Shah.
Okay, thank you, Satyaki. So let me, I think, share my screen. So is it visible?
Yes, it's visible. But can you make it full screen?
Sure. I can make it full screen. Yeah. Yeah, can you see now?
Yes, yes, it's a full screen now. Okay.
Okay. So, so good morning, everyone. So first of all, yeah, I would like to thank Dr. Satyaki Kaur for inviting me and yeah, giving me this opportunity. And yeah, Satyaki is a long time friend of us, and he was here for some time as a postdoc. So I know him quite long time by now. So today, basically, after discussing with Satyaki, so I thought that yeah, so it's let me not discuss about my specific works here. Rather, let me try to give a brief or picture or of this new field, which is called topological insulators and topological superconductors, which at least for last 10 years or so has become one of the very active and elegant field of research in modern condensed matter physics. So I decided that okay, let me give some introduction to this field and discuss about the basic phenomenology of this field. So let me do that, and let me try to do that, and then okay, then if you have questions, etc., that definitely will discuss at the end. And so before just starting, let me just um, acknowledge my collaborators. So mainly my 5 students who are at the top. Can you see my cursor?
Yeah, we can see that.
Okay, great. So my students and these 2 postdocs who work with me, and currently the other postdocs in other places, they are collaborating, and these 2 faculty members in Niger and Niger Kolkata are also has given a lot of inputs in the work that currently we are doing. But anyway, let me not discuss the specific works, but let us discuss about this field in general and the basic phenomenology. So let me start with some introduction. So in the introduction, and then so there's 2 topics. I have divided these 2 topics, which is topological insulators and topological superconductors. So I will try to give the basic theory, or not the theory, but the phenomenology of that. And at the end, depending on the time, how much I have, I'll give you some outlook that what are very new in this area, and and conclude my talk. So to start with, actually, so we need to recapitulate about some of our basic quantum mechanics. So one of them is so this concept will be needed as we go along with the talk. So this first one is the Dirac equation. So let me remind ourselves about this equation. So what I have written here is the Dirac equation. You can see that this Dirac equation describes the relativistic motion of spin of electrons, and where this alphas and the Dirac matrices is the momentum operator, beta is another matrix, and m is the mass term, and c is the velocity of light. So this equation, these Dirac matrices are complex matrices with complex elements, and in general, solving this Dirac equation, you get a complex solution of this Dirac equation, which is the 4-component, the spinors. So and if you set the mass term in this Dirac equation, then you can go to another representation, which is called the Wild representation, where you will have 2 solutions of these Wild equations. And the thing is that, I mean, now suppose you have the velocity of light, because it's a relativistic equation. Now, if you think that this velocity of light, if you just imagine that if I have a material in condensed matter where this velocity of light is replaced by the Fermi velocity, but this Fermi velocity has very high uh, velocity of the electron. Current velocity is high, such that it's very close to the, not close, but at least quite close to the velocity of light. Then, and if you define the Hamiltonian, here and the spectrum of that. So you can see that the spectrum of the spectrum of that material actually will follow the massless Dirac spectrum, where you have the valence band and the conduction band and the massless linear Dirac spectrum. So this information will need in the so I just give you one slide because to remind you that this concept will need. And another concept we'll need is the concept of Berry phase in quantum mechanics. So in quantum mechanics, when we study about that, what we say is that if you have a Hamiltonian, which depends on the, let's say, several parameters, but suppose these parameters are not static, these are time-dependent parameter, let's say, and if you want to solve the Schrodinger equation with this time-dependent parameters, so then what happens that if these parameters vary very slowly, slow in the sense that the variation is such that the system always remains in its ground state, and you ignore or you can neglect all kind of transitions which will take you to the non-equilibrium. But if you stay in the ground state even by this adiabatic slow variation of this parameter, and if you see the instantaneous eigenstate of this problem, then you will see that, okay, from quantum mechanics we know that it will have a phase or a function, but this phase will have two terms. So one term will be the dynamical phase that we always encounter, but there will be a new phase in that which is called the Berry phase. The Berry phase is very special because it is a robust, or it's a geometric phase, and it depends and it's a very topological object, a robust object, and this Berry phase has very non-trivial consequences in physics, in condensed matter or in other areas. So we'll discuss about the consequence of this Berry phase in band structure of few materials in our talk. So now this Berry phase actually you can write in this form. So where you can see that this guy is actually acting like a vector potential, so which is called the Berry connection. And if you have a vector potential, then you can define a fictitious magnetic field like a curl of this A, which is called the Berry curvature. So so this concept of Berry curvature or Berry phase will be essential for our talk. So for your information, as a example of Berry phase, I'm just saying that the Aharonov phase in quantum mechanics is one of the manifestation of Berry phase, and in general, to measure such Berry phase, you have to do some interference experiments. But in condensed matter, we'll have the implications of Berry phase in measurable quantities that I will show. So these two are the very basic concept that you will need. So now let us start about this field, actually, which started from 1980 from the theory, from the experiment of integer quantum Hall effect. So this field starts from there actually. So what happens is that it's a quantum Hall structure when we study in our first year of BSc, the classical Hall effect. So what we take is a 2D electron gas, and if we take a 2D electron gas and you apply a magnetic field which is perpendicular to this plane of this electron gas, and you apply a and so in the classically what happens is that the electric force and the Lorentz force due to magnetic field, when they come at the equilibrium, so at that time you set up a condition where you can define some classical Hall coefficient, which comes out to be the resistivity in that classical limit comes out to be the proportional to the magnetic field. But now if you perform this experiment in very much low temperature, so where in this 1980 experiment of von Klitzing, they perform this experiment at below 4 Kelvin and quite high magnetic field, which goes until 14 Tesla in this plot, and very high mobility sample. High mobility means almost the system doesn't have disorder. And if you see, so this Hall resistivity, which is a transverse measurement, if you see the Hall resistivity in this plot, which is this, you can see that for a low magnetic field, a small magnetic field, they follow a linear behavior, which is the classical limit. But as you go for high magnetic field and more in the quantum limit, then you see that you have some staircase feature of this Hall conductivity, and there are very clear plateaus uh, of this Hall resistivity or Hall conductivity. And these green things are the longitudinal resistivity, which is measured here. So that has these peaks here. So, what in this measurement, what von Klitzing measured is that the Hall is conductivity is actually a quantized quantity. Quantized in the sense that it is quantized in the unit of this E square over h, and this n is an integer. So it's called integer quantum Hall effect because you get quantized Hall conductivity in integers. And this is a very accurate measurement. So the error was around 10 to the power minus 9 in this measurement. So this is almost an exact measurement. And so the understanding of this phenomenology or this experiment actually later, I mean, after a few years, people actually found some topological argument behind this feature that we just showed in the integer quantum Hall effect. So how to understand that from the band picture? So suppose if I take an insulator, okay. So we know that in the insulators, electrons are tightly bound to the nucleus, so that you don't have, you cannot have electrical conductivity or transport through the system. And what happens is the band that you have a band gap here, those shear band gap, and no current, and no current in this system. So this is band insulator. So from mathematical topology point of view, this band you can think like a sphere or an orange here with the genus, which is a mathematical term. So G is 0. That means there is no there is a hole in this system. But if you think about the quantum Hall, so the quantum Hall basically is a problem. So now if you the problem is that, so you have to solve that particularly in a magnetic field problem that we studied in the quantum mechanics. So we know that what happens is that if I apply a magnetic field to the 2D electron system, so ultimately after solving this problem under some Landau gauge or choosing some gauge, that we get a harmonic oscillator solution in that. So 2D, the system behaves like a harmonic oscillator. So in the semi-classical argument, so you have the circular orbits in the bulk of the system. So they form these Landau levels. So these are Landau levels, the harmonic oscillator solutions. And you can see that if I fill until certain Landau level, so the highest filled Landau level and the lowest unoccupied Landau level has a clear gap, which is proportional to the cyclotron frequency. And in that sense, you can think about that I have a picture like an insulator here. So in the bulk, the system is an insulator, but these two insulators, the band insulator and this insulator, is very different, the mechanism. So in the mathematical topological language, this is like a donut. So these two, orange and the donut, is very different geometrical structure. You cannot deform the orange and come back to and go to this donut. But the interesting point is that these are circular orbits in the bulk, but if I go at the edges of this sample, then you have this skipping orbits in semi-classical, and which is unidirectional. So this basically not closed. So what happens is that the bulk is actually like an insulator, but at the edge you have a conducting channel of the system. So this is very non-trivial. This never happened in the band insulator. But here the bulk is insulator, but somehow in the picture I can see that at my edges I have in the upper edge you have a edge mode where the electron can propagate in the right moving way, or in the other edge of the sample is a left moving. So total in quantum Hall sample, 2 edge mode, so 1 plus 1 for the 2 edges. And these are robust in the sense that this edge mode, if you put an impurity here, your backscattering is not allowed. Because to allow backscattering, the electron has to be left moving after backscattering, which is not possible until and unless you go to the other edge, but the other edge is separated by this bulk gap of the Landau level in the system. So, and these are called chiral edge state because electron motion is unidirectional. So, and this is also called the bulk and boundary correspondence in the quantum Hall. So this is a pictorial, from the pictorial point of view, this is one of the understanding of the, and you can see that this edge mode actually gives rise to this quantized Hall conductivity. So if you have one edge, then you will have a first integer. If you have 2, 3, 4, depending on the filling fraction of your, depending on the number of Landau level you choose, you can have the number of edge modes and the corresponding quantized Hall conductivity. This is one of the understanding. But from a more mathematical point of view, from the bulk band, so I'm saying bulk boundary. So the bulk and boundary is really, actually there is a correspondence. So this bulk of this system is related to the, very non-trivial, related to the Bery phase. So as I have defined previously that the Bery connection, now if you think that the slow variation you are having in the bulk, in the momentum, let's say. So now you don't have time dependent parameter, but in the momentum space, you have kx and ky, they are somehow forming some closed paths, and these kx and ky are slowly varying. So the kx and ky gives you some block states. So if you construct from your band, if you construct your Bery connection and the fictitious magnetic field or Bery curvature using the block state, and if you integrate of this Bery curvature over the first Brillouin zone, then in this quantum Hall sample, you get a integer here. So this integral will give you some 2 pi n is some or integer, so you will get some integer here. So for an ordinary insulator, this integral will give you 0, absolute 0. But in quantum Hall, this will give you this integer number, and it can be shown that the transverse Hall conductivity is basically C into E square over H, where C is this called the Chern number. So first is Thouless and Nightingale, and the other two gentlemen, I forgot about the name, they showed that the transverse conductivity of the quantum Hall is related to the Bery phase, or the Bery curvature of the band, which effectively can be calculated by the Chern number prescription. So this is the way to look at it from mathematically. That so this quantum Hall is also called a Chern insulator, and the bulk boundary correspondence is that you have a bulk insulator, but at the edges you have non-trivial conducting metallic modes, which doesn't happen in an ordinary insulator. And it is related to the topology because of this Bery connection, which is a topological object. And also the edge modes, these are robust because they are immune to the impurity present in the system. So now the question in topological insulators, so what is new? So in the quantum Hall already has one kind of topological insulator. But now in the field of topological insulator, people started asking the question that, can I still realize quantum Hall effect without a magnetic field? So what is the thing that when we apply a magnetic field, then we know that it breaks the time reversal symmetry. So this quantum Hall state is a time reversal symmetry broken phase. But people ask the question that can I have quantum Hall effect without a magnetic field? That is, without breaking the time reversal symmetry. Okay, so can I have a time reversal invariant quantum Hall? So the answer is yes. And who are responsible for that? So you don't need magnetic field. But suppose if you have material where you have strong spin orbit coupling, the spin orbit coupling in quantum mechanics is L dot S, and we know that the spin orbit coupling preserves the time reversal symmetry. It commutes to the time reversal spin orbit coupling actually preserve the time reversal symmetry. And also in quantum mechanics, that if you have time reversal symmetry, then we know that it has time reversal symmetry operator has a degenerate solution, which are called the Cramer's pairs. So you will have the Cramer's pairs in your system. So in this topic, if you see this picture where I show a 2D topological insulator, where it's same as quantum Hall, the bulk states has behave like a band insulator. So the valence band and conduction band has a clear gap. But now the thing is that what about the edges or the boundary of this 2D system? So the quantum Hall, you had a unidirectional chiral propagating mode, metallic propagating mode. But here you can see that at the boundary, it is much more non-trivial, because here the electron momentum and spin are actually locked. That means the right moving electron can have, let's say, down electron, and the left moving electron can have up spin. The spin and momentum are coupled here. And the direction and the spin just reversed if you go to the other boundary. So it will be like this, and immediately, so these two edge modes are actually the Cramer's pair due to the time reversal symmetry here. And also they are not called chiral, now they are called helical. So it's like sigma naught p. So it's a helical edge modes, and they are time reversal symmetric partner of the time reversal symmetry present in the system. Also, another feature is that, so now if you think that this states has upspin with left moving, downspin with right moving, so the total charge conductivity for this system will be 0, because charge and up and down are propagating in opposite direction with equal amplitude. So now what will happen if you measure like Hall conductivity, then you will get a complete spin Hall conductivity here. It's pure spin Hall conductivity, no charge. So for that reason, this system, these states are called quantum spin Hall state or quantum speed Hall insulator. So there are many names of that. So that means it's a 2 copies of the quantum Hall. So you have 2 to 4 is 2 plus 2 at the two edges. And also these modes, again, they are robust against the impurity. And why? So if you put an impurity here, and if you want to allow backscattering, so the right moving can be left moving due to backscattering, but you not only change your direction of motion of the electron, but you have to reverse the spin also, which is not possible for a non-magnetic or scalar impurity. So this is robust against scalar impurity or non-magnetic impurity. Obviously, if you put a magnetic impurity, then immediately time reversal symmetry will be broken, and you will start getting backscattering. So this is this 3D picture. It's a 2D picture. If you generalize in 3D, so then in 3D the boundary is surface. So you get surface modes as metallic surfaces for a 3D topological insulator. And the intervening is that this 2D surface of a 3D topological insulator satisfy a massless Dirac spectrum, which I have shown before. So they follow a massless Dirac spectrum in the 2D when they are in the 2D surface states. But the bulk of this 3D topological insulator is completely gapped or band, like behave like a band insulator. And also in the surface of this 3D system is the electron and momentum of the electron, momentum and spin of the electron is coupled. So there is spin momentum locked. So now from this 2D picture, I mean this for the 2D topological insulator, let us try to understand this, what is the mechanism. So necessary mechanism to have this the feature. So from the practical point of view, this 2D topological insulator was first proposed in graphene, but as we know, the graphene doesn't have, the pristine graphene has very small spin orbit coupling. So that theoretical proposal was not possible to verify in experiment. So, but it has been verified in other material called mercury telluride. So first in the theory, what people have done in this system, that if you think in this picture that if you made one quantum well of this mercury telluride, which is sandwiched between two cadmium telluride material. So this cadmium telluride has been used to make this quantum well structure for this mercury telluride, and in this mercury telluride you have a very strong spin orbit coupling. And if you think about this two band, which is electron and hole band, let's say, so this two band and this two band, and they are separated by this gap here, and the width of this well is, let's say, some width d. And now suppose you start changing the width of this well, you change and change. So what happens is that you do spin orbit coupling, your band actually try to band will come close together. I mean, they come closer and closer, and after some critical thickness, they will invert. So what happens is that you will have a band inversion. So that means you have a band gap which was, let's say, positive here, or the band gap becomes negative in that sense. So you have a band inversion. So so when you have a band inversion in your band structure, so you will get so this is the necessary mechanism to obtain this 2D topological insulator. Also, obviously, not only this band inversion is a primary requirement, but also you have to see, so you have to define some topological invariant for the band structure of these materials, which probably I'm skipping here in this discussion. But like the Chern invariant in classical quantum Hall, here also you have to define some topological invariant, which one can define like a spin Chern number or Z2 invariant. But let's not get into the mathematics of these invariants, but just for your information that you have to define a proper invariant for this 2D or 3D topological insulators to characterize the bands of these systems. But at least from the band inversion point of view, you can see that when something is inverting, so it cannot invert without going to a zero. That means when you have a band inversion in this system, you will have a zero mode. So these edge modes or surface modes are the zero mode, which exactly appears at zero energy. So just to flash about the basic models. So as I said, the first model was the Kane-Meller model, which was defined in graphene, and the 3D model, effective model, but the actual model is more complicated, that is defined on bismuth solenoid. And you can see, if you see the edge mode of this model, you can see this edge mode with a dispersing edge mode with upspin and downspin coupled to it. So these edge modes are metallic, and these are all bulk states here. And here it's a surface. So this surface state, you can see this behaves like a massless linear Dirac spectrum, and they are metallic, but the bulk is insulated. But the main difference between quantum Hall and this is that they are time reversal invariant. So you need different invariant to characterize them, unlike the quantum Hall, which is a time reversal broken topological state. So let me show you that in experiment how they differentiate between these systems. Like for 2D, we already now know that these are edge modes. So they perform the experiment in the exact geometry of mercury telluride that I showed, and you see that when you are in the trivial band insulating phase, your conductance is very small in the unit of E square over H. But now when you're in the topological phase, your conductivity becomes 2 E square over H. So this 2 is coming because of the two copies of the edge, up spin and down spin, and the so three momentum locked edge modes is that as there are two edge modes, you're getting two, but in the quantum Hall you are getting only one. So here, and if you increase the temperature of the sample due to thermal fluctuation, the response is quite robust, but there are small thermal fluctuations here, but it remains quite close to the your to quantized value. So these edge modes, the helical edge modes, actually corresponds to quantized conductance of 2 square over h that they showed in the experiment, and which clearly explains that in the experimental point of view, one can distinguish between the trivial and the topological phase in the mercury telluride. And also in three-dimensional case, they perform some angle resolved photoemission spectroscopy, and they have shown the Dirac nature of the surface modes here. And so in this picture, you can see that here on the surfaces, your spin and momentum are actually locked. So you will get some spin texture here, because spin and momentum will follow in the Dirac cone, behave like this. And this spin texture also you can see in the planar picture in experiment. They also show this in the Fermi surface. You have the spin momentum locked motion of the electron. So this is picture. So what we learned so far is that topological, so quantum Hall, one kind of topological insulator, time reversal symmetry broken, but there are time reversal invariant topological insulators. For example, mercury telluride or bismuth solenoid. There actually I get boundary modes which are non-trivial, helical, and they are time reversal partner like Kramer space. And you have to define different topological invariant for the two cases. So far we discussed about insulators, but now if we ask the question that can we generalize this bulk boundary correspondence that I discussed in topological insulators in case of a superconductor. So the question. So before I go to the topological superconductor, let me just show you one slide of the what is a superconductor. This is for the students. That superconductors, our earlier speaker also gave you at the end some introduction, but here let me show you that a superconductor after a certain critical temperature, you can have a state in a system where in the superconductor the resistivity suddenly drops to 0, but from the microscopic point of view, in the superconducting state, what that is supercurrent is the Cooper pair. So Cooper pair is actually the 2 electron bound state at the Fermi surface, and this appears due to the electron-electron interaction mediated by the electron-phonon interaction in the system. And this kind of Cooper pairs actually can have different kind. So they can be like S wave. So K up and minus K down is like S wave, but also in the in the theory or in the reality, you can have other kind of pairing which are called P wave pairing. So in the P wave, your spin of the 2 electron bound state can be up up or down down, or it can be up down plus down up, like a triplet state in quantum mechanics. So this P wave pairing will be needed in our discussion. So Cooper pair is a 2 electron bound state near the Fermi surface, and what happens in the spectrum of a superconductor is that at the Fermi energy you open up a gap, or the instability of the comes as a gap in the system, which is the superconducting gap. So this, so you can see that now in a band insulator I have a gap structure, but the Bogoliubov-Dichin equation for a superconductor also solving that, you will have a gap structure. So the question comes into the mind that like an insulator, can I also have topological superconductor and get some more exotic phenomena? But to understand the exotic phenomena in topological insulators, we have to understand one more basics, which is called the Majorana fermion, because that is the meat in the story of topological superconductor, that one can have Majorana. So what is Majorana? So I have shown you the Dirac equation, and the solution of that Dirac equation actually gives you the complex solutions always. So, but Majorana asked questions here that in 1937, that can I have a clever representation of the Dirac equation? Of the clever representation means, can I have a representation of the Dirac matrices which only involve real numbers? And in that situation, what happens is that the Dirac matrices, they follows the usual anti-commutation relation, but what happens is that the Dirac matrices satisfy this condition, gamma is equal to gamma dagger. So which physically means that you have an electrically neutral particle which is of its own antiparticle. So for this Majorana or the Majorana fermions, your particle and antiparticle is same. So in particle physics, neutrinos was believed to be the Majoranas, but now we know that neutrino has mass, so there is no signature that one can say that neutrinos are Majorana. But people started asking the question, can I have the signature of these Majoranas in the solid state systems? And you can see I have given a lot of reviews where you can see the discussion of the development here, and topological insulators topological superconductors, they actually play a crucial role to understand the emergence of Majorana in solid state systems. And the application of Majorana is that this is a very new, happening topic, is that so these Majoranas will follow non-abelian statistics. That means they are not like bosons, not like fermions, and they are objects, and they can be the building block of quantum computers. So these are belief, and people are doing research in that. Anyway, I am not the expert of particularly this field, but as an example, one can think about people are looking at this. But for us, the theoretical interest is that, can I realize Majorana in condensed matter systems, and what will be the signature of that? That one has to see in the experiment. So now, so then you ask the question that okay, I understand superconductor. Okay, I get about the picture of Majorana. So then why superconductor is important if we want to see Majorana? Then the question is that for a superconductor, if you for a spinless or p-wave superconductor, chiral p-wave, if you write the Bogoliubov quasi-particle operator, you see that if you have a S-wave, then you will have the spin here. But if you have a spinless, or let's say both are same spin, so what this equation tells you, that the Bogoliubov quasi-particle you have written in terms of electron and a hole, and these are the amplitudes. But now, if it happens that suppose these amplitudes of electron holes, suppose they become equal, UN is equal to V star. So then, due to particle hole symmetry present in a superconductor, at zero energy, this operator will satisfy this condition. So this is the condition that you get from the Majorana representation, but this same condition you can satisfy in case of p-wave superconductor, where at zero energy you have this gamma is equal to gamma dagger. That means particle and antiparticle are same in condensed matter point of view. Antiparticle is like a hole. So that means you can expect that I have a gapped structure. That means I have an kind of insulator, and also in a p-wave gap, like the p-wave superconductor also have this gap. So within a p-wave gap, I can satisfy this Majorana fermion condition at zero energy, and then I should get a Majorana kind of mode at zero energy. So the outcome is that in case of superconductor in condensed matter, what happens is that within this p-wave gap, you have a zero energy state. So like Majorana fermion in condensed matter is like a zero energy state here. This is the zero energy state. So it appears as a bound state in the system. And at the bound state, you satisfy this condition. Gamma is equal to gamma net, Majorana condition. So in the 3 dimension, it will come as a bound state at the vertex core of the superconductor. But what I will discuss is the appearance of Majorana as a mid-gap state like this at the interface of or at 1D system. So let me skip that. What are the other systems where people have found Majorana? Let us come to a system where actually in 1D I can have this realization of Majorana. But anyway, take this model as a very theoretical model. In the next slide, I will show that how to realize that in a more practical situation. So this is called Kitaev chain. So what Kitaev did, he took a tight binding model. So you have a chemical potential, you have a hopping in the lattice, and you can see that you have a spinless superconducting pairing here. So you have like a p wave, so it's like a chiral p wave, like up or down, or effectively spinless in that sense. So this model in 1D, and what he thinks that, okay, he go to a clever basis. So he write the fermionic operator at each lattice side as a superposition of 2 Majorana operator. So this is the representation, or this is the basis that he chosen. And sometimes actually it happens to a very handy basis. So now physically, if you see that at each lattice side, each fermion will have 2 Majoranas. So that means with the 2 Majorana, with the 2 Majorana operator, I can actually form a complex. I can form a complex fermion. So if you think about it, if you go to a phase where the hopping T is not equal to delta, in that phase, what happens is that at each lattice site, 2 Majorana forms an electron. So this is called a trivial phase. But now you go to another phase in this 1D model where the 2 Majoranas at the adjacent lattice sites form single electron, but there are 2 Majoranas that are left behind. So if you look at this Hamiltonian, actually in this basis you can diagonalize this Hamiltonian in the real space, and if you see this Hamiltonian, you can see that in this Hamiltonian the gamma 1 and the gamma n2 doesn't appear. So as if this 2 Majorana will form a non-local fermionic state, a non-local state, not fermionic. They will form a non-local state because they are sitting at the 2 ends of the chain. So here one of them, the other one of them here. So this is very non-local object, this operator. So this is called the 2 unpaired Majorana at the 2 ends of the chain. And as they don't appear in the Hamiltonian, you can think that these two, for example, as if they're at 0 energy. So these 2 Majorana forms a non-local state at 0 energy, and from the quantum computation view, these are important because in quantum computation, one want to intend to carry information non-locally. So that means if I have something at Calcutta and something at Delhi, for example, but still I want to transmit in a computer the signal. So these are, and so why topological? Let me come back in a minute. So these are very robust objects. So these are topological mode, neutral, Majorana mode. So these are actually non-local state that appears at 0 energy. But this model, in a realistic, there is no material, or there is no system where I can really engineer, or I can really see a material where I can have this model. But theorists and experimentalists, they try to engineer this model in a 1D system. So in a 1D system, simplest, what you can check, you can take a nanoware. This is a 1D object. So what is the theoretical proposal? And then I will show the experiment in a minute. So what people take, they take a single channel nanoware in this picture. And this nanoware, you choose a material in the nanoware where you have strong spin orbit coupling. So this is Rajkot spin orbit coupling. And also you apply a Zeeman field, but you apply the Zeeman field such that the spin orbit direction and the Zeeman field should be perpendicular to each other. Now, the question is that this nanoware, okay, that I can choose, that I can apply magnetic field, I can take a material for nanoware with a strong spin orbit coupling. But this nanoware is not superconducting by itself. So now how to bring superconductivity in this nanoware? So so even if this material is not superconductor, what you can do, you can place this nanoware in close proximity to a bulk S-wave superconductor. So then what will happen that due to proximity effect, and the mechanism is tunneling of Cooper pairs in the nanoware, what can happen, it depends also how the interface is, you can actually induce superconductivity in this nanoware. But if it is a S-wave superconductor, or S-wave pairing will be induced in the system.
Excuse me, Arijit, sorry.
Yeah.
So you just have 5 more minutes, is that fine?
Oh yeah, I'm fine. I'm done.
Okay. Thank you.
5 minutes is fine. Okay. Thank you. So from the band structure, if you look at that, in the spin orbit, in presence of spin orbit, the band, spin up band and spin down band are separated, the blue and the green, and the magnetic field opens up a gap at the k is equal to 0 here. And now, so if you increase the strength of the magnetic field, effectively the two spin bands are now separated. And if you choose your chemical potentials as that, here, so you can see that the chemical potential will encounter an effective p-wave pairing. So inducing S-wave actually and choosing the chemical potential properly, I can engineer a p-wave pairing in the system. And due to that, so that means like a Kitab chain here, and I can have this 2 Majorana mode. So from the wave function point of view, is a Majorana at these two ends, the Majorana wave function is actually localized. Localized means they have a small tail inside the nanowire. Obviously, if you take a very short nanowire, so this to tail can overlap, and then they will become a fermion. But you have to choose the length of the nanowire such that they are spatially separated. So this is the interesting point, that you can have a Majorana in this 1D system, and which exactly people have engineered in a real experiment. So these are 3 experiments I am showing. This is a very recent experiment in the system, exactly what I showed you. They experimentally developed that, and they have shown that if you look at the tunneling conductance of this system, so they have chosen indium antimonide, which has strong spin orbit coupling, and as I have told, the Majorana appears at the 0 energy. So if you change the bias of your reservoir, so at 0 energy, due to Majorana bound state, you have a quantized conductance of 2 square over h. So here also in the 2D plot is the same. In the trivial regime, there is no signal. You change your magnetic field such that you enter into the topological regime, where it behaves like a K-type chain. I have a pairing and the Majorana signature coming out as this 2 square over h. So this is the indirect signature. So the 0 bias peak can come from other reasons also, but at least they claim that bypassing the other reason, not bypassing, arguing the other reason is not possible in the experiment. This can be an indirect signature of the Majorana. And these experiments are done at very low temperature, like 20 millikelvin. So, okay. So Shatoki, I think 2-3 minutes?
Yes, fine, yeah.
Yeah, so I'm at the end. So as an outlook, so I just want to show you that what I discussed so far is the topological insulator superconductors, which has one, from the bulk it's insulator, but the edges have 1D or 2D boundary modes. But you can have, like it's a new appearance in the field, you can have topological insulators, which are called higher order topological insulators, where you don't have your edge or the surface is actually gapped as well as the bulk, but you can have boundary modes at the hinges of the system or at the coordinates. So that means if your dimension of the system is d, and then you can have a topological insulator of nth order. That means in a two dimension, if n is 1 in two dimension, you get a usual topological insulator. But if n is 2 and d is 2, you get the zero mode or the zero dimensional mode, which are these are like corner modes. So these are called second order topological insulator. Similarly, in 3D, you can have choose n is equal to 2 and n is equal to 3. The correspondingly you will get hinge modes or corner mode, like second order 3D topological insulator, third order 3D topological insulator, and these are. But the bulk of these systems are very, very different, and one has to really characterize this system, but with very different mathematical prescriptions, etc. But these corner modes are also, again, like Majorana mode, they are very localized here. They cannot carry current. To see them, you really need an STM probe to see the signal of them. But the thing is that they, again, non-local objects and can be very useful in quantum computers, etc. But these are all under investigation at this moment, that how to characterize higher order topological insulator, how to realize higher order topological superconductor, what will happen, and a lot of this is a very new field, a very new area, very new field in this subfield of this topological insulator. So there's a lot of research work is going on. So at the end, so what is your take-home message? Is that topological insulators, so these are class of materials which are characterized by a bulk bandgap, like an ordinary insulator, and but they have conducting states at their d-1 boundary. So that means if I choose d is equal to 2, then I will have a 1D edge mode, and if I choose d is equal to 3, I have a 2D surface. So this boundary state emerges as a time reversal Cramer's pairs due to time reversal symmetry, which comes due to the presence of spin orbit coupling, which preserves time reversal symmetry, unlike magnetic field in the quantum Hall case. And one has to define different topological invariants for that. And also these boundary modes are insensitive to scattering by non-magnetic impurities. And experimentally, first the 2D topological insulator was realized in mercury telluride, and in 3D it was in bismuth selenide. So these are the basic take-home message. And then from the topological superconducting point of view, the more exotic part is that you can have the Majorana fermion that appears in case of a p-wave superconducting chain, and one can really design or engineer a p-wave pairing, effective p-wave pairing in a 1D spin orbit coupled nanowire with Zeeman field and proximity induced superconductivity. And this two non-local Majorana bound state, so it appears as a bound state in case of condensed matter. They're protected by particle Hall symmetry, and they appear at the two ends of the nanowire. So effectively, they form a very non-local state, which is protected by particle Hall symmetry and protected by the bulk superconducting gap. And from the experimental point of view, is zero bias peak because they appears at zero energy. So the zero bias peak that appear in the tunneling conductance signal, that reveals the indirect experimental signature of Majorana bound state. Also, I am not saying that what I am showing is a smoking gun signal of Majorana, unless and until you show that the experimental evidence of non-abelian statistics or some other very concrete signature, it's very hard to say that this is really Majorana. So the debate is going on, the research is going on. And at the end, I mean, if you want, so I have not discussed anything about my work, specific my work here, but these are the fields. So currently the higher order phases I am working on. So these are the, but you can, if you want to look at my publication list, you can go to this link and have a look at the papers. So at the end, thank you for your attention and patience. So I end here. So let us discuss.
Thank you so much, Arijit. Actually, you gave a talk on a very specialized topic, but that's a very nice presentation. And you touched upon many important things that most of us, like students, and also sometimes us, have difficulty in understanding, like chart number and all those, Majoran and all those stuffs. So I think we have some questions. Dr. Saurabh Haldar from Maths Department. So can you just look over the question answer session?
Yeah, sure.
Yes, Dr. Kaur, thank you. And also very thanks to Dr. Shah. So we have a few questions from the audience that first, Mr. Somnath Jalal has made a query that if energy is proportional to mod k, then is it always the signature of topological states or age states?
No. The answer is absolutely no. So, so getting this gapless spectrum doesn't mean that the system is topological. Okay. So the thing is that you have to look at the bulk bands of this system. So the bulk states, the bulk block state has to satisfy some topological invariant depending on the symmetry of the problem. Okay. So like graphene also shows the massless Dirac spectrum but it is not a topological insulator because the bulk is gapless in case of graphene, and also there is not. I mean, if you calculate the invariant, so for the gapless system, it will come out to be 0.
Okay.
So getting linear spectrum doesn't mean that you have topology in the system.
All right. Mr. Anupam Banerjee has made another question that can you please explain Cooper pair again or give some reference in this respect?
Sure. Yeah. So Cooper pairs actually is a 2-electron bound state that carry a supercurrent in a superconductor. So this Cooper pair actually arises, or so the previous speaker also mentioned that the formation of Cooper pairs, the microscopic theory is called the BCS theory for conventional superconductors. So, so it appears due to the, so suppose if you have a system where you have electron phonon coupling, so now if one electron so one electron can have a attractive interaction with another electron if they come due to the lattice vibration or the electron phonon interaction in the system. So one can actually show that there is a time scale within which this attractive interaction dominates. So that means, so if you have attractive interaction, then we know from quantum mechanics that you can have a bound state. So this 2-electron bound state due to the effective attractive interaction forms a Cooper pair. So for a reference, I can suggest that the book by Tinkham, Theory of Superconductivity by Tinkham.
Okay. So Mr. Jalal has made another question that electrons have both charge and spin. So how in the age of 2D sample, spin current is there and charge current is gapped? Where is the charge degree of freedom for the electron?
So in the H mode, you have charge degree of freedom and spin degree of freedom both. So I have shown that the electron has right moving electron has a down spin. So so spin momentum is actually the locked. Okay, here. So in these edge modes. So now the question is that here, so if you define the charge current like the current due to the upspin plus current due to the downspin, and spin current like current due to the upspin minus current due to the downspin, then from this picture you can see that in the effectively, what will happen that as the upspin and downspin propagate in opposite direction because of their direction of motion. This is the charge. Okay, so I up and will be of the order of I up will be exactly equal to minus I down. So in that sense, the charge current will be 0, but this spin current will be finite, pure. But the charge and spin both are there. It doesn't that it disappears.
Okay.
So the current due to the upspin and downspin will be opposite, but both degree of freedom is here. Only in the bulk, okay, bulk is gapped, definitely. Yeah, if I understand the question in this way, then this is the answer.
Okay, and can you write the name of the book in the chat box? That is a question from one of our viewers. So that I think he mentioned that that book as a reference you already have told us.
Yeah, sure. I am writing.
Or you can also tell the
Yeah, you
book.
can just tell us. You can just write.
Yes, yes, yes.
A theory of superconductivity by. I am writing.
Okay.
Yes, yes.
Income.
Tinkham. So that's all about the queries from our audience and participants. So I over to Mr. Dr. Kaur for the next.
Hello, sir. Hello.
Yes.
Hello.
Hello. Should I ask a question?
Yeah, sure.
Sir, in the case of the question about Professor Somnath Jalal, in the case of ESR spectroscopy, we know that the orbital angular momentum we choose the material in such a way that the orbital angular momentum cancels each other and only the spin angular momentum remains. Is this does this has any correspondence with the questions about Somnath Jalal, sir? I mean, how the charges current is not present, but the spin current is there.
No. As I say that it's not that the charge is not present. Charge is present because you have a right moving electron which is coupled to. So right moving electron can have only downspin, let's say, or the left moving electron can have only upspin. Your spin and momentum are locked. Okay, at the edges. The charge degree of freedom is there.
Okay, sir. Okay, sir. Thank you.
Okay.
So if there is any other query from our participants, you can also ask Dr. Shah.
Yeah. Thank you, Dr. Halder, and thank you, Dr. Shaha, for this nice presentation and also this interacting question and answer session. So thanks for finding time for us.
You're welcome.
Then I hope that if we need you again for some other talk,
Sure.
you will again listen to us and come.
Yeah, thank you.
So,
Thank you for hosting me, Satyam.
Yeah, thank you so much. Okay, so now we will move to our next talk. So the two keynote speeches we had today, we already have today. Now we have some two short presentations. So the first short presentation will be given by Mr. Anupam Shaha. So Anupam is a student of our college. He did his BSc from APC College. I think there are many students from APC College today here. And then his master's he did from Adamas University. And after that, he started working as a junior research fellow under a DST ACRV scheme in our college for almost 7 months by now. So he will be talking on Fermi level fluctuation, magnetization, Zeeman splitting during quantum oscillation in nodal line semimetals. So Anupam,
Yes, sir.
You can take over the session and then deliver your talk. So
Okay, sir.
stage
I'm
is yours.
presenting my slide. Sir, is my slides are visible for all?
Yeah, it's visible.
I'm Anupam Shaha. I'm working ZRF in DST ACRB project under the supervision of Dr. Sattwikar. First, I want to say thank you to the organizer of the international webinar to give me the opportunity to present my short presentation at this topic, the Fermi level fluctuation, magnetization, and Zeeman splitting during quantum oscillation in nodal line semimetals. So those are the following are the topic content of my topics. I go through this by slides. So first I talk about according to electronic band theory, we classified the materials. For metal, the conduction and valence band, the gaps are zero and they are overlapped. For insulator and semiconductor, the gaps are larger and smaller. In semi-metal, some wave vector, discrete wave vectors, their energy gap is zero. And for others wave vectors, the gap is non-zero. So it is also important when the crossing are both the crossing are linear and at the point of their connection, so there is a effective mass is going to be zero and there is a high mobility to the particle. So going to the crossing linear crossing case, we going to the Dirac equation, which is a relativistic case. I am not rather than going to the Schrodinger equation. So here it is a Hamiltonian for massless Dirac equation, typically for graphene. So here it produces two contact, and it is called the Dirac point. And due to the degeneracy at this point, it makes the dub the it is a semi-metal. It is a 2D picture. It is a 2D discussion. If we go specialize in 3 dimension, then we go to the Hamiltonian resembles as this equation, and in this equation, the Weyl fermions. It is those are the Weyl points connection, and as it goes the Weyl fermion, those are propagating as parallel, anti-parallel to their spin, and for their chirality, and after without Dirac equation and Weyl fermion, there is also exist a non-zero gap for nodal line semi-metal system. In nodal line semi-metal system, the conduction band and valence band touches and they makes a line and a closed path. And it is also observed in some materials like JDAR, SIS, PBTIA2, and other than the this is the nodal line semi-metal system, and the nodal line semi-metal system, the linear crossing at this point. So at this point, as you can see, so they mix like this, and the connection is closed in a loop, and then it is make a nodal ring, as you can see here mentioned in this pictorial representation. So the nodal ring or loops appear when symmetry constraint allow band crossing with linear dispersion and along lines in brilliant zone. So one cannot just vanish the nodal line for some deformation of the systems. It can be big or less, but it cannot be vanished, and this is called, and that's why it is a topological robust nature. And also there is a some mathematical tricks, as my early speaker Arijit sir also said about all those things. So I am just going through this as a mathematical form. So Berry connection, Berry curvature, and Berry phase. So just putting an electronic path on the nodal line some position, so one can calculate the Berry phases and also from the sum of the Berry connections curvature, one can also get the Chern number. So the Berry phase, if the Berry phase is non-zero, then it is called the system have a non-trivial topology, and if the Berry phase is equal to zero, then it is have a non-topological nature. And also the Chern number is defined in not zero, then it is a local order or non-local order parameters is defined. So the quantum oscillation can measure the from the quantum oscillation of those system, one can also measure the Berry phase easily. So that's why we are going to the quantum oscillation of such of the systems, and we are going to our systems. So here is a brief introduction to quantum oscillation. So what happens when electron in a magnetic field? The electron goes the electronic cyclotron motion in semi-classical treatment. If we go to the momentum space and going to discuss about the what is happening in momentum space, then there come to Landau quantization. I am not talking about all those mathematical expression as those are mentioned in the slides. I am just talk about what happens physically. So for magnetic, in absence of magnetic field, the electron states are uniformly spaced and distributed, and they are equally spaced by the value 2 pi by L. So for this case, it is here the absence of magnetic field. But when we switch on the magnetic field, then the electronic states are coalesces, and from the square structure they are rearranges in a circle, and those are labeled as a Landau level. For this, for first I say that for this first circle here it is a n equal to 0, and after that is a n equal to 1, 2, 3 and higher for order, and here it is also. Then what is happen for switch on the magnetic field, or square states are just coalesces and they are formed like a circle, and it is indices as a Landau tube. In mathematical form we can also define as a as you can see the laser pointer, that E equal to n plus half h cross omega. It is a Hamiltonian, it is the energy for the well known harmonic oscillator, and you can also, it is equal to the, for the case here it is for absence of magnetic field, it is E equal to h cut k square kx square plus ky square, not for kz. So if we include the kz form, that is a third direction forms, and what is happen, it is just shifted a height, and it is formed like this Landau tubes, and those are called the Landau tubes also. So now I discuss about the quantum oscillation using the Onsager relation. That the label of for some energy, the energy must be equal to the extremal surface of the orbital. So from this I can say that it is here it is a one tube and Landau tube, and for some height kz, the energy is E function of kz. Now here the if the tube I just shell in a E and E plus d energy shell, then here there is a no energy which is equal to the extremal orbit. So then the same construction is done for the third picture, and here we see that there is a energy E which is equal to the extremal orbit, and for this there is a peak in density state. You can see this straight line. So in and then it is false like a one-dimensional density of states, as you can see the typically plot of the density of states. This plot is for the fix the magnetic field and just vary the energy expression. You can typically get this density of state plot for say for each Landau level. So here is also mentioned is that. So it is our theoretical model. It is a Hamiltonian for where it is a nodal line semi-metal system Hamiltonian with time reversal and space inversion symmetries are there, and it is the 2 by 2 matrix. As you can see, the sigma are the Pauli matrices for degree for spin degrees of freedom. And if we diagonalize the Hamiltonian, we get the energy expression, and here is a plus minus sign is indicate the conduction band and valence band. So if we how we can define it is a Hamiltonian, it is a nodal line system, semi-metal system Hamiltonian. If you just put the energy gap is equal to 0, then the locus of the system is that Vpz equal to 0, and also the this term is also equal to 0. So the P perpendicular is basically the px square plus y square. So what we have px square plus py square equal to root over 2mm0 m star. So this is basically the equation of a circle indicates that. So that's why I call there is a system for nodal line semi-metal system. For this timing, we just put on the magnetic field, and due to this presence of magnetic field, there are some mathematical calculation have been
Anupam,
done. Yes, sir.
you have 5 more minutes.
Okay, there have to be done, and you can see these Landau states and the Fermi surfaces as also defined for this corresponding Hamiltonian. So now we just put a Zeeman term. We want to study how the system will behave when we put the Zeeman term. Zeeman term nothing but the number and is a half z mu b. And after previous calculation, we also define those equation. And here is a Hamilton is a 4 by 4 matrix, and where the sigma and tau are the define the spin and orbital degrees of freedom. And this is a typical picture, and it is a picture of this Zeeman term. So now we go to the nodal line symmetry system and quantum oscillation. So what happened in this case is mentioned in the picture in this paper. So in this paper, there is calculating the how to discover the quantum oscillation. So it is just put the extremal orbit, and then he just put the for how the chemical potential energy. So you can define this perpendicular for Landau levels, and also for you can calculate the Landau Fan diagram. This same things also done for this paper, score paper also. For in this case, there is a periodic nature in the magnetic field. So you can also go to the picture. I'm just showing how our work is. So our work is how the Fermi level fluctuate in our system. So it is the we get this picture figure from this expression from all the calculation. We are just going to thermodynamical point of views, and also calculate in zero temperature analysis. So as you can see, the Fermi fluctuation for low the magnetic field value, it is dominates, and for it is reduces when the magnetic field value is less, and it is periodically. So we just study the magnetization, how the magnetization is work in our neutral line symmetrical system. As you can see, the amplitude of the quantum oscillation is more reduces when the magnetic field is reduces, as the all the expression are calculated from thermodynamics point of view, and one can also calculate these values also. And then we going to the effective mass variation in our nodal line symmetrical system. As you see in the first in the expression of energy, there is a plus minus term, and also there is a plus minus term due to Zeeman term. So there is a if the effective mass is nearly equal to m, then there we have a condition for pz equal to 0. Then we have putting n equal to 0, then the Zeeman term is the Zeeman term contribution is large. So if we just large, and if we n equal to 5 or 10 higher level indices, then there is a contribution is reduces. But if the effective mass is reduces, then the contribution is also large. As you can see, if the if it is for the pz equal to 0 situation, but if the pz equal not equal to 0, then also there is m0 as a non-zero value. Then those are also considered, and those values are we are numerically calculated and also plotted in this case. So first of all, the MR is the ratio of the effective mass and electronic mass. As you can see, for here we take the z equal to 2 values as a z factor, and in the bottom case we are just put the effective mass ratio is just 0.025 as mentioned in this paper. So what we observe here is that the dash line is due to the Zeeman term. So for this energy expression, there is also energy variation in the spectrum. As you can see, we get in the energy expression the plus minus b term. So there is also a splitting. So in the density of state in our nodal line system, we get this picture. There is a two variation for the effective mass is effective mass. The ratio of the effective mass and electronic mass is nearly equal to unit. Then we cannot observe or distinguish the peaks of the density of state. But if we reduces the ratio, then we can distinguish the peaks. So here you can see that for without Zeeman effect, it is the peaks for which is shown as a black color. And then if we just introduce Zeeman term, then we have this part is just split in two parts, and we can differentiate this. So this our work in summary, I am just also saying all this. So just in summary, I want to say that in our future, just in our, I would like to say that the nodal line symmetrical system for perpendicular nodal plane, just report any topology, just does not report any topological oscillations. So we are just planning for the magnetic field which is acting on nodal plane, and because we can just examine the effort for the effective mass g variation and also Fermi level fluctuation for topological magnetic oscillation occurring, all of this. So this work is funded or they are supported by the DST ACRB project, and I am also thanks to Dr. Satyakar who is giving me the opportunity to work with him at this project. So thank you, and you have any questions, so please ask me. And also thank you for your kind attention also.
Thank you so much, Anupam.
Yeah,
That was a good presentation, but I would prefer you to spend more time with your results rather than
Yes,
the elaborate introduction.
Yes, sir.
So
Yes.
the time is very short.
Yes, sir. Yes, sir.
So if there is any question, then we can have
Yeah, hi,
any
Anupam.
question.
Yes, sir. Yes.
Can you tell me that what is the reason behind the oscillation in your density of
Uh,
state?
yes, sir. Sir, the quantum oscillation is a reason for this is that I can say this. Quantum is a reason for this that we have Landau tubes like that, and we have Landau levels and their corresponding cross-sectional area, as we can see in on-second relation. Yeah, and we are also note that the labels are also H cross omega c, so there is a B term. So when we changes the magnetic field, the Landau level cross sectional area also changes, and it successively crosses the Fermi surface. So for this, we are all know that at zero temperature, at the Fermi surface we have a stress, electronic stress, but out of the Fermi surface there is no stress. So for this, if this there is a electronic, there is a extremal orbital state, orbital cross-sectional area, then for this case we have a large number of electron states, and thus we have a peak. So if it is a periodically occurs, so then we have a some as you can see the density of state peak. So for some for when the Landau level cross-sectional area are crosses the Fermi surface, then we have a peak, and for
Yeah.
this we have a quantum oscillation behavior.
Okay. So in your case,
Yes, sir.
can I show
Yes, sir.
me?
This picture,
So,
sir.
no. So in which gauge you are working?
In this paper, as you can see, score paper, there is showing the quantum oscillation and nodal line semi-metals. And we are just working on Fermi level
Oh,
fluctuation in our nodal line semi-metal system. Here is also there is a change in number, and also we are chemical potential versus 1 by V, the periodic nature we can also study. And in
so
this
you
paper,
are
you can also.
starting from the while. Okay, so can I start?
Yes, sir. Yes, sir. Yes, sir.
Should we start from around the while Hamiltonian and choose a magnetic field? So like
Sir, we are working on a nodal line semi-metal system. As you can
yes, so
see,
you have
it
a
is our.
loop. You have a loop.
Uh, Please say again.
So then you will have a nodal line. You will have a loop at each point. You have the Dirac.
Yes, sir. Yes, sir. So it is just a crossing, and then it is going
Acha.
through the closed loop. So it is
Ah,
called
sure.
nodal ring also. Nodal ring shape.
Oh, acha. This is the starting Hamiltonian, the
Yes, sir.
continuum model. I
You
see.
can also see from this pictorial representation, as you can see, this is the point. So, and in while fermion, this is the 2 points, while points, but in nodal ring case, there is a in this picture also seen, it is the crossing at this point. And if you just close this path as like this, as you can see, there is a nodal ring also. So for the conduction and valence band, the touches are just like this closed path. So thus it is called nodal ring.
So you are calculating the so for the entire system, not around the ring, I guess, because your starting Hamiltonian has the quadratic spectrum, and you have chosen Landau gauge.
Yes, sir. We are just choosing the Landau gauge, asymmetric Landau gauge.
So from this oscillation, I mean, can I say anything about the contribution due to the nodal ring? Because all contribution is coming from the entire bulk.
Actually, Arijit, if you consider just a 3D electron gas, then if you keep on changing the magnetic field, you will see that pattern of the density of states that
Sure.
will keep on repeating. So that is the oscillation, quantum oscillations when you see it in the electron gas system.
So you are trying to see this for this 3D system, like H0. If I think about that, this
Yeah,
H0 is a typical continuum model for you.
yeah,
And
and then he put the magnetic field first along first perpendicular to the nodal plane, and then along the nodal plane.
okay.
And then when he does that, that Landau quantization occurs, so the spectra changes. So basically, and then from there you
I
can see the
understand.
yeah.
Okay. Sure. Yeah, I'm fine. Yeah.
Okay, sir. Thank you.
Okay, so if there is no more question, then we can just go to the last talk of the day. Thank you, Anupam.
Thank, thank you, sir.
So the last talk, the last short presentation. The speaker's name is Dr. Pompa Pal Goswami. Uh, Dr. Goswami did her BSc in physics from BB College Asansol, and then her MSc in physics, pure physics from Jadavpur University, and thereafter she did her PhD from SN Bose National Center for Basic Sciences. He got his PhD degree in 2015, and right now she works as an assistant teacher and also a student in the B.Ed department at Vijay Krishna Girls College at Howrah. So today's topic of her presentation is preparation and characterization of magnetic nanoparticles for industrial and medical applications. So Dr. Goswami, hope you are here.
Uh, yes, sir, I am here.
Yeah, so if you can just now start your presentation. Thank you.
Okay. Good morning, everybody. Let me share my screen. Today, the topic of my presentation is preparation and characterization of magnetic nanoparticles for industrial and medical applications. So this is my plan of presentation. And so what is a nanoparticle? A nanoparticle is a small particle that ranges between 1 to 100 nanometer in size, undetectable by human eye. Nanoparticle can exhibit significantly different physical and chemical properties to their larger material counterparts. Most nanoparticles are made up of only few angstrom. And magnetic nanoparticles are a class of nanoparticles that can be manipulated using magnetic fields. Such particles commonly consist of two components, a magnetic material like nickel, cobalt, iron, and a chemically component that has functionality. In my system, rather in our system, we have chosen nickel and iron as magnetic component, and chromium, which is chromium and manganese as a non-magnetic component. Manganese is non-magnetic in nature, and chromium is anti-ferromagnetic in nature. So we have extended our work to make thin films of these systems. Like we have already worked with NIM and NIFECR alloys, and we have found huge applications of these systems. So we have extended our research to make thin films of this alloy system, because these 3D transition metal alloys like these systems are of great importance due to a variety of their physical properties and consequent applications. These are very prospective materials for use in nuclear fusion reactors due to high corrosion resistance and potentially small radiating swelling. This can also be used as buffer layer in high density magnetic storage devices. So we can say that these systems, the systems with nickel nanoparticles are of great importance today, and for many applications like medical, environment applications, and fundamental issue, and to know fundamental physics as well as in industry applications. So how we have made how can we make these thin films? There are different techniques or different methods by which we can prepare thin films and magnetic thin films. These methods are like chemical vapor deposition, thermal deposition, vacuum thermal evaporation, molecular beam epitaxy, nuclear beam evaporation, but we have chosen PLD technique, that is pulsed laser deposition technique. Why? Because there are certain advantages on this system, on this technique. What are these advantages? We can find the flexibility and of wavelength and power density. The pressure range can be controlled from 10 to the power minus 7 millibar to 1 millibar. We can control the growth rate of deposition. We can use different materials for deposition one by one, and any materials can be produced by using different target materials. So uh, this is the advantages of PLT technique. And after preparing, we have to characterize it. So how we can characterize it. First of all, I want to say that these alloy systems were prepared by arc melting process under argon atmosphere. After preparing these alloy systems, we have to make thin films of these systems. So the nanocrystalline of these particles like NiMn and NiFeCr particles can be embedded in a matrix using pulse laser deposition technique. So we have to choose a substrate which can be diamagnetic in nature, silicon or sapphire, whatever substrate we can use, and the experiment should be done under a high vacuum environment, that is 10 to the power minus 7 torr. And the substrate temperature will be kept around 600 degrees Celsius during the growth process of nickel iron chromium on the matrix. The energy density and the repetition rate of the laser beam should be used 2 joule per centimeter square and 10 hertz respectively. So after preparation of these thin films, we have to characterize it by different instruments like MPMS, BSM, ACM, EDX, XRD, and STMZ. So what can we do with these instruments? Like magnetization measurements can be performed using MPMS quantum designs with magnetometer operating in the RSO mode. The size distribution of NiFeCr particles and NiMn particles and the crystalline quality of both the matrix and the magnetic particles will be investigated by cross-sectional high-resolution scanning transmission electron microscope with the atomic number contrast, because as we have different atoms like NiFeCr, so we have to know which atom is where. So we can use STMZ instrument. The microstructure of the films will be characterized by the X-ray diffraction technique. So we can get the diffraction analysis we can have the XRD pattern to determine the crystallographic structure of the material, and by using EDX system we can microanalysis the chemical components of the systems we have prepared. So magnetic characterization can be done by vibrating sample magnetometer and also the screen magnetometer and also the PPMS system. So this is the phase diagram. Already I have done on NiMn system. If the phase diagram shows changing the concentration of manganese from 15 to 37%, we can see the phase change of magnetization. Like for the concentration of 15 Mn%, we found two different magnetic phases like ferromagnetic and ferrospin glass. So we can see that magnetic phase diagram of disordered alloy system shows different magnetic phases like ferromagnetic, ferrospin glass, conventional spin glass, paramagnetic, and antiferromagnetic regions. So we have done another. We have chosen another system to experiment, and which is NiFeCr alloys. So already experiment has been done on alloy system. So our next target is to do to prepare thin films on this system and change and check the difference of phases of both the systems as their bulk counterparts. So this is the XRD we have done to know the crystallographic phase. So the peak shows that this is FCC in structure, and there is no double phase. This is the single phase FCC structure. The lattice parameter we have calculated, which is around 3.54 angstrom. Since the addition of small amount of non-magnetic substance, here we have used chromium, changes the magnetic phases drastically. So we have to know which component is in what percent. So we have used EDEX technique to know the chemical component of the elements accurately and found it satisfactorily. This is the composition diagram of the ternary alloy at 10K. So what it says? It says that this is the composition diagram at 10K. So at 10K, which material is paramagnet, which material is ferromagnet, which is antiferromagnet or ferrospin glass. We can see this from this picture only. Also, there is a straight line which represents both zero line magnetorestriction and Hall conductivity lines, which theoretically predicted from the speed band model. While the other line with considerable curvature is the experimentally observed line at 10K. It lies much below the theoretical line. So, this would be negative for all the ferromagnetic samples. And the ferromagnetic increases with the increasing chromium concentration. So, it has been noticed that with increasing chromium concentration and decreasing iron concentration, the system moves towards the antiferromagnetic region from ferromagnetism. So this is very useful. I have told already. We have done experiment on the. We have started experiment on doing experiment on this. And there are huge applications of these thin films of both nickel manganese and nickel iron chromium alloys. So these can be categorized like fundamental, industrial, and biomedical. So to know the fundamental physics as well as magnetization, this system is very much useful, like ferromagnetic, ferrospin glass, conventional spin glass, paramagnetism, and antiferromagnetism regions in these two systems, like NIM and NIFCR system. So quite naturally, they are very interesting to know the basic physics and magnetism. If we control the size and shrink it to nanoscale region, we found drastic change in magnetic behavior. This will help us to understand the basic properties of magnetism. There are industrial applications too, like this can be used as low cost, environment friendly data storage device, magnetic recording media, magnetic refrigeration, and magnetic sensors to measure very small amount of current. Using PLD technique, that is pulse laser deposition technique, the size of these nanoparticles can be shrink even more smaller to get our demand fulfilled. To say about biomedical applications of nanoparticles, there are biomedical applications of these systems are tremendous. They can be classified into two categories, like inside and outside the body, and can be used in diagnostic and drug delivery systems. So we can conclude that if we shrink the thickness of the thin films, or even we compare their property with their bulk counterpart, we can find the great difference in their magnetic property as well as in daily life use. It can be observed that even addition of a smaller amount of chromium to this system, and even a smaller amount of addition of manganese to the system with the system of nickel, the phases of the system can be changed drastically, and which also reduces the corrosion property. These films can be used as the buffer layers of spin valves and can be used in biomedical application, like surgical tools, communicating pipelines, position detectors, current measurements devices, etc. So these are the references I have used. Thank you for your patience.
Uh, Thank you so much, Dr. Goswami, for a nice presentation. At least for your presentation, we get at least one single talk from the experiment side, because most of the previous talks were on theory. So I'll just see whether if there is any question. Yeah, there is one question. Dr. Somnath Jalal has asked, what is spin glass? And what is the quantity we measure to say that the sample is in spin glass state?
Spin glass is like one type of randomness. Like we use glass. Glass means very much random. The particles are very random. Here, spin glass means spins are randomly oriented, and we can change the state from spin glass to in a certain order state. We can find a temperature. Below this temperature, the spins are wholly disordered. I think we cannot even manage the spins with the application of the magnetic field and whatever we can instrument we can use. So spin glass is a magnetic property. Below spin glass temperature, that is freezing temperature, we cannot control the spins even with the application of a higher magnetic field.
Yeah, but it also had a second part, that what is the quantity we measure to say that the sample is in spin glass state?
We have to measure the magnetization. That means magnetization, the AC susceptibility also changes in different way. Unlike ferromagnetic, ferromagnetic, antiferromagnetic, the AC susceptibility of spin glass is different from that of the others. So AC susceptibility we can use.
Okay. Thank you so much. So, is there any other questions? Okay, so if there is no other question, then I will again thank the speaker, Dr. Goswami, for coming here and giving her talk. So thank you so much. And so that was the last talk of today. So we will close today's session here. And thank you everybody for your active participation and asking questions, and then being patient and then listening to the talks. So just to remind that this is not over, we have another day. So we will be back at 10 a.m. tomorrow, and the joining link will be given to you again via email. So thank you so much. We'll just formally close the session here now. Thanks again. So you all can now leave the session whenever you want. Thank you.
Thank you, Satyapita.
Thank you, Shomnath.
It was a very nice session.
Yeah, so waiting for tomorrow's session.
Okay.
With your all
Bye.
big talks.